For decades, the global strategy for carbon has been spending billions of dollars trying to capture it, tax it, and bury it out of sight. But when we look at the sheer volume of material being moved, treating carbon dioxide as a waste product appears to be a massive oversight in how we manage industrial feedstocks. A century ago, early oil refineries dumped gasoline into rivers because they were focused on kerosene. They were discarding the very commodity that would eventually power the global economy. Carbon dioxide is a concentrated source of carbon. Currently, we are simply leaving that raw material in the wrong part of the supply chain. To see the scale of this unused resource, we look at India, where industrial expansion is happening faster than almost anywhere else on Earth. Every year, India emits approximately 2.7 billion tons of CO2. These emissions are not just coming from millions of scattered tailpipes. They are pouring out of massive, localized industrial clusters in high concentrations. When these facilities vent this gas into the atmosphere, they are releasing the same carbon atoms that were just mined, transported, and burned at a massive capital cost. Our current energy model is linear. We extract carbon from the ground, burn it for power, and release the exhaust into the sky. This requires a massive physical footprint. We spend enormous amounts of energy just digging ever deeper into the crust for new carbon sources. Carbon utilization changes that trajectory. Instead of digging, we intercept emissions at the smokestack to create a circular loop. But capturing gas creates a logistics problem. Without a use, you end up with millions of tons of trapped gas. Captured carbon only has value if it can be transformed into products the market is buying. Completing this cycle requires technology that can reverse engineer the combustion process. This is the focus of our proprietary IP. We are developing the chemical systems required to act as the bridge in this utilization loop. The process begins by taking captured CO2 molecules and chemically stripping them apart into individual carbon and oxygen atoms. We then take those isolated carbon atoms and introduce hydrogen, recombining them to form stable hydrocarbon chains. These synthetic hydrocarbons are chemically identical to conventional fuels. They can power existing engines and power plants without requiring a new distribution network. This same chemical foundation allows us to manufacture advanced building materials, locking captured carbon into the physical structures of our buildings and roads. This technology converts the exhaust that causes warming into the physical fuel and infrastructure we use every day. This shift in engineering redefines the global economic landscape. By synthesizing fuels and materials, carbon moves from a liability that companies pay to get rid of to a tradable asset class that they can sell. The financial scale is significant. The global market for carbon utilization is projected to cross $1 trillion as these synthetic products reach parity with extracted ones. Eventually, the profit generated by selling captured carbon will create a stronger incentive for emission reduction than government regulation ever could. Returning to India, we see how existing infrastructure determines the winners of this transition. India's industrial clusters currently represent a massive concentration of emissions. Under this model, those chimneys become pre-built harvesting centers for raw carbon feedstock. By integrating this conversion technology, India can transition into a primary exporter of synthetic fuels and carbon-based materials. The challenge is no longer how to eliminate carbon, but how to use it profitably. Now that the technology exists to turn exhaust into fuel, are you ready to invest in carbon as a commodity?